Okay, welcome everyone. Just before starting the seminar, a couple of introduction of new people. One of them is Pedro Monroy, who will be here. It's a fellowship from the Scholar project for doing the whole physical.
And well, mine is announcement is also the new person that is incorporated in IFISC for a few months because it's high. It's Javier Moreno that's here. I will be going to this event. So 2 months. Then well, I mean let's start with the seminar and perhaps also an introduction. You're not going to get. So it's a pleasure to introduce you, Andrea Lancicchinetti. Actually, we met some time ago in Turin. He did there and we could take it to Turin because it's an institute of research, not a university. And then after that, he has been as a postdoc in the lab of Amaral in Western University in Chicago. It's the difference. And then when he finished that in a couple of years, he moved to a place that is far up in the north. He will show us where it is. It's the ice lab in Umeå University in Sweden. Because I don't know where this this is. I mean, he has been working almost from the PhD in questions about clustering networks, community detection. It's a pleasure to have you here. That's the first.
Thank you. Thank you. So it's a pleasure for me to be here. Actually, it's a very beautiful place, and coming from the north, I can see finally the summer. So it's really nice. So by the way, so today we're going to talk about memory, network flows, and applications. So as you can see, there are quite a lot of keywords in the titles, but I will explain them as we go. But first of all, as I promised, I have to tell you where I'm coming from. So this is Stockholm, and it's 600 kilometers. It's very up the north. Okay, so going back to the actual keywords of the titles, today we're going to talk about memory network flows. And first of all, what do we mean by network flow? And as you can see, there are all the nodes are these white dots, and there are the connection, which is the flat connection between the airports. The interesting thing is that the topology of this graph is actually very interesting. And the reason is that, well, we don't have flying cars, so we cannot fly from any pair of nodes in this system. Well, at least not yet. First, if there are no connection between Anchorage, which is up here, and Umeå, where I came from, because not so many people do that, and that would be too expensive, and therefore people have actually to find an efficient way to navigate in this system. And because of that, somehow the airline companies self-organize and build up a structure so that the way I actually travel from Umeå to a small place in Alaska, which is even smaller than Umeå, is something like I go from Umeå to a topology of the network sets a constraint on the flow. So by flow, in fact, we mean all kinds of things that can somehow navigate through the topology of the system. Anyway, the airport transportation network is an example. Here, today, I will talk about some other examples. In particular, I will talk about a little bit network of citations, so that the nodes are journals, and the links are citations between journals. We talk about emails, where the nodes are people, and the connections are the network. So it's a very different system because while the airport transportation network, the connectivity has a broad distribution, a small to big networks. In a lattice, all the nodes have exactly the same connectivity. It's exaggerate, so every node has just 6 neighbors. And then I will talk about hospitals in Stockholm, and here the nodes are departments in the hospitals, and the movements, and the links are movements of patients between different departments in the system. So this is all example. So it's how things move on the top of the technology. So here is a very classical example of a model of flow. It's unfortunately the figure is a little blurred, but this is a random walking dimension. So every point here is kind of tiny, but it's a lattice in 2D. And if you like make steps at random, you can go in it's a 2D, so you can go either north or south, east or west, and you do a lot of steps, and then you end up with something like this. So this is a very simple model, and if in the limit where the steps are very small, we get the primary motion. I think probably all of you are pretty much familiar with that. For instance, how particles diffuse in fluid. Well, you assume that pretty much they do a random walk, because if there is symmetry, there is no reason to believe that going west is more likely than going east. And therefore, it's actually a random walk, and there is no memory. Particles don't have a brain. If they go left at a certain point, they might go right or left at another point in equilibrium. This model is actually used quite a lot in all the systems that we described before. But in that case, we make an assumption which is quite strong. We make an assumption that people are very important to move at random. I mean, Jose knows that this is an assumption which is actually used a lot in epidemiological models, for instance. It's an assumption that a random walk without memory actually holds in a system like hypothetical station actor. So how can we check that? Well, the way we check that is that we look at how things move in all the real systems that I was talking about just a moment ago. So starting with the airport, this is possible because there is a website which is called RITA, the Research Infrastructure Attention. And if you go to the website, they will give to you for free all the tickets of, not all, actually it's 10% of all the tickets which have been purchased in the US. I think we have the 2011. And the way it can look like is pretty much like this. We have, for instance, we have found that roughly 50,000 people bought a ticket from New York to Chicago back to New York, and so on and so forth. So a ticket here is what we call a pathway. It's just basically a sequence of steps in the network. And you can immediately more likely they will go back to New York rather than go to San Francisco. 50,000 people compared to 1,000. So in a sense, this gives the idea that probably a random walk is not the best model to describe this. But we will talk about that more in a second. In the case of the emails, we also have pathways. We also have itineraries. How we do that? Well, imagine that Alice sends a message to Bob. Then we can look at the subject of the email, and we can see if Bob will reply or forward the email to somebody else. If he just replies, that will appear in the dataset. Yeah, I forgot to tell you that this dataset is from the Umeå dataset, which is this big company in France, which basically made all the emails of the employees and partner of the messages, which we look at this. So kind of similar to New York, Chicago. In the case of journals, do we have pathways? Well, in a sense we do. The way we can build pathways among the journals is the following. Imagine I have a paper in PRE, which is citing a paper in PNAS. Now, you know that PNAS is a multidisciplinary journal. There are a lot of papers from different disciplines. But if I'm in a certain paper in PNAS, which has got a citation from PRE, and now I pick a reference from this paper, where do I go? Well, it's more likely that I will go to physics journal than to ecology journal. Okay? So let's say that, for instance, I go to PLF. Why is that? Well, because the fact that before I was in PLE is telling me that this paper in PNAS is about physics, in a sense. That's this whole one. We will see that actually. So in this way, like looking at pathways of citations between articles aggregated at the level of journals, we get the pathways between journals. So we know if a tax is in a certain grid, in a certain point in this grid, we know where it's going next. So that's how we can build pathways. So somehow this is a similar example to the 2D and the walk that we showed before. But as you can imagine, taxi drivers hopefully are not drunk, so they will not go back and forth. That actually is actually holds too. And then in the last case of the hospitals in Stockholm, we have the movements between departments. So what happens is that patients and so on, and so very often then they are sent back to the department which were possible before. So in this case, we can actually track how people move between different departments in a hospital. I cannot say much more about this because they are anonymized, as you can imagine. But yeah, so we actually have the pathways in that case. So how do we check if there is memory in these pathways or not? So the way we do that is, okay, we start from the raw data, and from this we can take the standard approach of building up a network. how do we do that? So, New York, Chicago, New York. This means that there are connections between New York and Chicago and between Chicago and New York. And this is the number of connections I have. So if I chop all the itineraries in two pieces, I get a simple network. But it's not the only thing I can do. I can do a little bit better, and I can chop the itineraries in three pieces. So instead of cutting this twice, I just take it as it is, and then I have a trigram. This is how it's called, which is basically an itinerary which accounts for from the fact that this number. So if I have a diagram, this is just a simple network. It's the standard approach that people have used for quite a long time. So all the nodes here can be visualized as circles, as you know, and then the arrows are telling me the probabilities of going from, for instance, from Chicago to New York, and that's all I have. When I have a trigram, the visualization is a little bit more complicated because, by the way, this is called first order microprocess. First order because where I will go next only depends on where I am now. Depends on where I am and where I was one step before. So the way to visualize it is that the state of the system is not just the physical node where I am now, but the whole state is described by a pair of nodes. Where I am now, let's say Chicago, and where I was one step before, let's say Seattle. So the whole state, if I'm here, it means that, okay, I'm in Chicago, coming from Seattle. Where I will go next, well, in this case, I will most likely go back to Seattle. And in this system, which we call memory network, the state of the node, the state of the system is a memory node pair. But the advantage is that what is a second order microprocess on a standard network is actually a first order microprocess on this system. Because where we go next only depends on the state of the system. This is pretty much the mathematical framework we use. And well, it's a nice illustration. It's not really new. Actually, Shannon already thought in these terms something like 60 years ago.
Sure question. The fact that the numbers on the first column, on the first table, and the one of the diagrams does not.
A lot more, because I also have a trigram which is, say, Chicago, New York, Chicago, which I don't have. But okay, let's say that I have Chicago, New York, Chicago. When I chop that diagram, the second part.
No, I'm referring to the first one.
Why
Chicago, New York, and New York, Chicago, New York.
Yeah, so.
So the and the diagram. Why they don't coincide, isn't it?
Because there will be something else. There will be something like New York 16 lines or something.
Yeah, this is a fraction of that very long ticket, which is.
Yeah. So every time I see New York, Chicago, New York,
in anything you.
I will put it.
Okay.
So that's why I have actually not so many more, but a little.
Yeah, well.
Okay, so when I want to, now the question is it really necessary? Does the second order microprocessor really does something better than a first order microprocessor? Well, one thing I can look at is, for instance, take the example of before, Chicago, and look at how the flow will mix. So in a first order microprocess, if I'm in Chicago, the probability that I will go to Seattle coming from Seattle, so I'm coming from Seattle, I'm in Chicago, what's the probability I will go to Chicago? The first order microprocess predicts 13%, which is pretty low. The second order predicts 83%. So in a sense, flow is much more constrained. It's much less mixed in a sense. I will quantify this better in a second. For the journals, the situation is actually pretty similar. So if I'm in PNAS, so this is a multidisciplinary journal, I'm in a paper, and this paper was cited by Plant Physiology. Given that, the probability that I will cite Plant Physiology is actually 36%. But if I don't remember that I was cited by Plant Physiology, I would predict only 70%. And you can see that nicely, a paper published in PNAS, getting a citation from a good. Quantify this better, of course. So here there's a table. I include a new system which is called cities. It's very similar to the airports. The difference is that some airports are in the same city actually, like Chicago Air and Chicago Midway. And in the cities, we just aggregate that. So if two airports are closer than 40 kilometers, now they just become a single node. So it's a system which we believe is somehow closer to reality. And to quantify the difference between first order macroprocess and second order macroprocess, we can look at the two-step return rate. What is that? It's the probability that I will go from A to B back to A. What I was showing you before, basically. And you can see that in a random walk, the probability is always smaller. In random walk memoryless, random walk is always smaller than with memory. There's one exception, which is a taxis. Well, and you can immediately see why. It's because if I'm going from a place in a grid in a certain direction, like here, it's much more likely that we keep going in the direction rather than back or the other way down. This can all better quantified looking at the entropy rate. And what is the entropy rate? It's basically a measure of how many bits of information I need to describe the movements of the random walk on average. So to give you some context, in the example that I was saying before, so imagine I have a 2D random walk on like this. So at every time step, I have 4 possibilities: north, south, east, west. In that case, the entropy rate would be 2, because I need 2 bits of information to say when the walker will go at every time step. It's either 1, 1, 1, 0, 0, 1, 0. So if I actually take what is called exponential entropy, so the entropy is the logarithm or the effective number of the neighbors, in a sense. If I take 2 to the power of the entropy, I get a measure of the effective number of neighbors of the network. It's something in the middle. And what happens for the, this was 3.5, is for the journals, is that with a second order macroprocess, you have 11 neighbors with a second order. With a first order, you have 22. So this means that if you account for memory, effectively you have a lot fewer neighbors than if you have memory. Why? Because somehow where you will go is much more constant. So this is a measure of, well, entropy in a broad sense is a measure of disorder. So what this is telling you is that second order macroprocess is much more ordered than first order. And you can actually make a scatter plot, which I think is pretty interesting, where on the x-axis you have the entropy without memory, and on the y. But it's kind of interesting to look at 2 things here. First of all, we did a randomized test where we take the real itineraries and we shuffle them around to check if you have enough data to support that the difference is significant with respect to the model. Because what can happen is that if you have really few data, it can happen that the drop in the entropy can be just a fluctuation. But it's not the case for most nodes. The blue ones is significant, the value of 10%. So you can see that that's not, the drop is not the same for all airports. The drop in the entropy is much stronger for Las Vegas than for Atlanta. Well, why is that? So if you take Las Vegas, the entropy without memory is up to 5. That means that effectively Las Vegas is connected to 32 airports. And with memory is connected to 8. So why is that? Well, it's because Las Vegas is used as a target. So a lot of people, there are 195 in the US. It's very easy to predict where you will go next, because most likely you will go back to where you come from. In the case of Atlanta, instead, there is not a big difference between first and second order, because Atlanta is used as a hub. So if you are in Atlanta and you come from New York, where you will go is hard to predict, because you will use that as a hub, so you can go to Los Angeles, or you can go back to New York, almost the same probability. So there is not a big difference between the two orders for Atlanta. So somehow it is telling us a little bit the difference between number of flows and memory. Now I would like to talk a little bit about applications of these ideas. And as I was mentioning before, the topology of the system, how things are connected, sets constraints on how things move. So that's like an arrow in this direction. But the interesting thing is that when it comes to application, somehow you can study dynamics to infer some of the property of the network. And a very typical example, well, these are 3 applications which are widely studied in network science. Ranking is maybe one of the best examples to illustrate that. Well, of course you know Google, and Google is using the PageRank. PageRank is exactly in Google. Now, yeah, it's very complicated, but at the beginning, the ranking was based on the probability of finding a random walk in that node. So just the most central node was somehow the one which was showing on top of the page. So this is telling you that somehow a dynamical process can be used to infer the structure, something about the structure of the network. And this is what I will talk now about. And the whole idea is that all of these applications use random walk typically. And now I will tell you what happens when you upgrade these applications from a random walk without memory to a random walk with. And things will change a little.
I have a question.
Yep.
I mean, if in a random way that has some memory.
Yes.
So this is not like if you want to use an adapted PageRank, it's not just counting the number of travelers in each airport.
So
and then you don't have to do anything.
I mean, in the case of the web, yes, you could do that. There will be probably a correlation between the number of users that find that page and the random walk. Of course, the two things will not be the same. The point is that we don't really have that data, right? We don't really know how many people are there. Yes.
For the airports, you do.
For the airports, you do. So you could use that. Actually, that would be still different because, well, we can talk about this later, but first order, I mean, everything is a model. So first order will tell you something which is close to how many people are there. A second order will tell you something which is even closer. If you use a third order model, it tells you, eventually you will get exactly how many people are there, because then the model will be so complex that actually, because that's, I mean, in the US they say there is a difference between where you cast the net and where you catch the fish, which means basically that you don't want to say where people are, but you want to tell people where they want to be. So somehow I think Google thinks that the PageRank is a better algorithm because it can predict where people will go rather than where they are, in some sense. So this is, I think, yeah, you can use that, maybe that's too much. But yeah, we can talk about that later. Okay, so going back to, yeah, starting from the first, which is a community action. Oops, okay. So in the case of community action, well, how can we use dynamical the nodes in groups and categories? So if you have a network like that, well, you can kind of see that probably here there are 4 groups, like one here, and so on. And an elegant way to find the groups in such a system is to look at basically if a random walk will get trapped in a subset of the nodes for a long time. So of course, this is a broad definition, and one needs to somehow model this and quantify it better. And the way that this has been done is by an algorithm which is called the IFISC, which was developed by one of the authors of this work. And the way this will work is a little bit technical. I just want to give you a rough idea. You can give to each node an ID. This is pretty much typical information theory problem, how you compress the information that is in the random walk. Well, the way is that you have to give IDs to each node, and you want to give small, like shorter IDs to nodes which are visited a lot, because that will make your string short, right? It's like, well, in English, short words are used more often, because somehow humans recognize that using that is more efficient, right? Like articles and verbs. And here it's kind of similar. So you have a node which is visited a lot, then we get a much shorter code word. This doesn't tell us what the clusters are, but a way ID of the cluster, and the suffix is the ID of the node given the cluster. So that gives basically, if you use that coding scheme, for instance, this cluster will be called 0, and if I'm there, in a certain node there, I have to say I'm in this group 0, and then I'm in this node 0, 0. This is basically just a way to code where the network is. And what happens is that the most efficient way to describe where the network is will be if the communities, if the clusters are tightly connected. So this requires some more time to digest it somehow, but I just wanted to give you an idea of how this works. The adopted to move from a first-order microprocess to a second one. And these are the differences we found in the airport network. So with a first-order microprocess, you only find two groups, which are pretty much east and west of the United States. In the second-order microprocess, you find a lot more structure, and interestingly, this node here is Las Vegas, and it belongs to a lot of groups. Why is that? Well, it's because people, as I was telling you before, people pretty much from wherever in the US, we go to Las Vegas, have some fun, and come back. So because of that, Las Vegas is put in a lot of different modules. But a node like Transit, that means that all the nodes in this group are tightly connected. But Las Vegas is a target. That means that Las Vegas is not connecting different parts of the system. It just belongs to different modules because the flow will be something like this or something like this. So somehow it doesn't mix. And this is what the algorithm is telling you. If you look at journals, this is also pretty interesting. What happens is that in a first-order microprocess, PNAS is classified together with cell biology, only cell biology, because most of the papers in PNAS are actually adopting microbiology. When you upgrade the model to a second-order microprocess, PNAS is 80% biology still, but also math, ecology, statistics, and so on. So somehow you find a similar, actually more groups are found too. This doesn't hold always. Specific journals like ecology or plant cells still belong to a group. So you find this overlap only where nodes actually belong to multiple groups, but otherwise the algorithm will not fit. Going back to PageRank, okay, so we did the PageRank on the journals only because that's probably the most interesting case. And what we found is actually a kind of interesting thing, is that this is basically the difference between first and second order. So if you are on the right, this means that you are gaining flow, you are gaining probability of being visible, so you are somehow having a better ranking. And if you are on the left, you are losing. And these are the top gainers, these are the top losers. And science is actually the second journal which loses most of the ranking. And the question is, so if you are in a journal like, PNAS has a lot of ranking, it's a big journal, a lot of citations go there. And all this ranking will go to molecular biology mostly. And will not go to physics because if you are in PNAS, you will most likely cite molecular biology. In the secondary process, this mixing doesn't happen, and specialized journal will gain more because if physics gives some credit to PNAS, this credit will go back to physics. So there is a destination. And because of that, interdisciplinary journal lose. More like plant cell and cell biology lose too, because so this is somehow.
What is the first and the last?
The first or the last? This one?
No, the first and the last.
The first is analysis of mathematical statistics, and the last one is annual statistics. Yeah, this might be because, so I'm actually not totally sure, but this must be related to the fact that this is a much more specialized journal than this one, if you are a statistician. I guess. But, yeah.
Surprise.
Okay, and then last application is about spreading. So, once again, so what is spreading? Well, spreading means basically that you look at how, for instance, an application is in public health, you look at how disease spread to an actor. And once again, random walk are used quite a lot in that case. Or in a physical node, like Chicago, you will talk to everybody. So it doesn't matter where they come from, because if you are in Chicago, it's a well-mixed population. So you will talk to people from all places. But the movements are second order. So the way the model works is you are in Seattle, for instance, you go to Chicago, you will spend some time there. Here we assume that you spend roughly 2 days. So every day with probability of 50%, you will move, or probability 50% you will stay. You will talk to people randomly, and then you will pick the next location with, either with the first order microprocess or with the second order microprocess. The model is SIR, meaning that you have, well, you're familiar with that, you have three categories, either susceptible, infected, or removed. And the typical pattern that you see is something like that, where here you have time, measures number of days, that, well, you see the infection somewhere, either Anchorage or Los Angeles, you will see time, the number of infected people will grow and then decrease because then you will have more and more removed people. This kind of classical thing. And then we did that with or without memory. So the blue is first order and the red is second order. And the two plots are for different R0, which is basically the parallels, how parallel it is. And you basically don't see any difference. So this was a negative result, which was a bit puzzling for us because there's quite a big difference in the data apparently. But when you do that for, as I was saying before, where you are in the physical node, you will talk to random people. So there is a lot of missing time there. And it doesn't matter where you come from, you will talk to people coming from all possible directions. So somehow the memory is not conserved during the transmission in the physical node. So that's part of the story. The other part of the story is that the return flow is it's kind of high. I mean, a lot of people go from a place, say Chicago and back, but it's not 100%. On average, it's only 50% in our data. And actually, if you remove all the tickets which are not return flow, which are not in the form of A to B and back to A, then you actually get a kind of big difference. So return flow is not high enough that somehow you can see a difference. If it was 100%, you would go back to a kind of commuting system where you actually see a difference. But in our data, no. Another thing that we tried was with emails, and in this case, the model is simpler. In the SLR model before, there were actually population of nodes, so there were people sitting on each node. In the case of emails, we are more thinking of a process like information fusion, and what is infected is not, I mean, infected are the people can get infected if they get an email with some content, let's say. And in this case, we see an email, there's an email with some kind of news, a gossip or a rumor or something, and then this infected email can be sent to somebody else, or you will reply to it, or you will forward it to some people, if it's a second order process. Otherwise, with the first order, you could just send it to some weird person. And this is the probability, we were like tuning the probability of using a first order Markov process or a second order. And you can actually see in this case that with a first order Markov process, the spread is actually lower. This is somehow expected because there are more constraints on the flow. But yeah, that doesn't happen for the mid-population model. Okay, so in conclusion, memory matters, not always. Not actually always. Like for the spreading, it's not the case. So I think people from
you are now doing models, right?
Yes.
This second order Markov process.
Yeah.
Now, how do you update the models?
How do I
Update.
what do you mean? I mean,
if you are talking now of a model, you're doing a simulation, right?
yeah. So basically,
And you have a dynamics on a given network.
yeah.
And then you need to specify your update order.
Is that okay? We get the real data. So this work is mostly empirical. So we have real data for each of the system. The data looks like that. From this system, just at once, we build either a standard network, like chopping the itineraries, or we build a memory network, chopping the itineraries. That's what we do. And actually, there is not data going on. I mean, once we have the data, the network is like quenched. That is. Yeah. And then once we have that, we measure things, entropy rate, return flow, or we apply this. Once we have the network, we can like run the community detection algorithm. But the network is not changed in time. It's fixed.
I understand. And now, when you go to the models,
If you
you
are
are updating them.
yeah. There are people.
What is the update rule?
So the update rule in this case is
when
that
you use the second order Markov process.
yeah. So in the first okay. So if I have people flowing, well, in the first Markov process, if I'm in Chicago, the update rule is like, okay, now I have to choose a location. I will choose a location proportionally to how many people it will move from the data. So if I have, if from the data I have a transition probability of 50% from Chicago to New York, the probability 50% people will do that. In the second Markov process, I have the transition probabilities too, but they are not from physical nodes, but they are from memory nodes. So basically, I have numbers for each memory node. I have like, given the time in this state node, the probability of going to Seattle is 40%, the probability of going to New York is 10%, and I will throw, like I toss a coin.
No. He's answering you of the updated of the position of the individual.
Yeah.
You are asking about the infection, the number of infected people.
The number of infected people.
For this is always a first order Markov process.
Yes.
Infection process is always a first
Yeah,
order.
for the infected people, yes, it's a, well, there are two steps. No, there is the reaction and diffusion. The diffusion is what I said now, and the infection is always first order. So no matters how people come from, because I think this is more realistic. I mean, I'm coming here from Umeå, right? But I don't talk to people from Umeå all the time.
But if you come from Germany, you will be taught with Germans. This is the fucking Mallorca.
We have to change the model to a paradigm. Yes. Yeah, it's for sure the one mix assumption is a strong assumption. Yes. So maybe before questions, maybe I just want to say, well, all our work actually relies a lot on his work that he did 6 years ago. He was actually probably the first to look at he was looking mostly at zero and first order Markov process. This is an example that is actually in his original paper, and I find very fascinating. So back and forth is like, you take language, but his paper, by the way, is called The Grammatical Theory of Communication. It's a masterpiece, I think. And he compares two models, as we do, but he compares a zero order and a first order, instead of first and second order. In a zero order Markov process, you just pick words at random according to the frequency of the words. There will be a noun, and then after noun there will be like a communication and so on. So all of a sudden the things makes already a lot more sense. The interesting thing about this is that he didn't really have computers at the time. So the way he was simulating this was using a book of random numbers, which I find really fascinating. And you can imagine opening a book that are only random numbers from some experiments. Yeah, so conclusion, these are the people I worked with. Martin Rausbal, who is actually the guy who invented Infomap. This is PhD student, Sistemas, Jimmy West from University of Washington, and then Ron Block from University of Namur. Yeah.
Thanks, Andrea. Questions?
So for the networks, you have two aspects, right? You can focus on the memory, and the other aspect is the temporal. The links are coming and going, right? So it seems that for the SIR, the memory is not so important, right? This is what I understood. So, but how this compares with the temporal aspect? So it's more important the temporal aspect than this memory, or depends on the kind of processors?
So in this case, we imagine, I was saying before, all the positions, all the probabilities are fixed, so there is no temporal aspects going on. I know that people are doing that, and they actually find interesting cases where temporal aspect apparently might matter more. But, so, to be honest, I'm not really reading that literature too much, so it's very hard to have a delay in the peak, even if you erase a lot of links. So this side which is somehow closer to our work. Even if you delete links, the spreading is a very robust process. It's very hard to contain it unless you really shut down all the world. This is pretty much a message which is pretty clear from very basic models. Somehow, I think this is what is going on here. When you have a secondary Markov process, somehow you are reducing the connectivity of the network a little bit, but this is for sure not enough to see a significant difference. When you do this, then you only account for people going back and forth, then you are reducing connectivity a lot more, and then you start seeing a difference.
Okay, well then, thanks Andrea, and he will be here. This is my office, so if anyone wants to talk to him or